me first introduce why the scope of the talk and why the scope of the talk is the way it is. A few years ago, when I was still in college, and I wanted to learn a lot more about Linux kernel modules. And as you will see in this presentation, there are a lot of cool things you can do with Linux kernel modules. Things like hide a file or even prevent root, which is the administrator of the Unix on Linux world, from getting access to a file, for example. These are just one of the things you can do. And when I looked at a lot of backdoors that were out there, a door is a famous one, and I looked at the techniques they were using. A door is basically a backdoor which tries to hide. A backdoor is something, as you probably most of you know, is something you install on a machine that you have configured, and it helps you maintain root access on that machine. So when I looked at the door, I found a lot of cool things that I wanted to learn about, but at that time I wasn't familiar with kernel programming or even LKMs and such. So I attended a few talks that talked about what LKMs are, but unfortunately talked about concepts. But when I walked out of there, I still didn't know enough to go back home and write my own Linux kernel module. So hopefully, in this presentation, I will do enough hand-holding and spoon-feeding so people with minimal C programming skills can go home today and hopefully write their own Linux kernel module. Let me first start off with why it would be why games are cool. I don't know about you, but to me, when I studied computer science, when I would try hard not to fall asleep during classes, I would compensate for that by looking at more technical topics and looking at source code. And there are a lot of things that I was confused by when somebody was explaining the concept to me, and when I actually looked at source code, even the comments in the source code, because they were exactly the way things are laid out, and I find doing actual work helps you understand operating systems more than anything. So if you're somebody who always wants to know about system programming or operating systems in general, LKMs are a great hobby. Kernel programming LKMs is basically you are doing kernel programming. Because the Linux kernel module, once you load it, runs in kernel space, and the code is loaded into kernel memory, so it becomes a part of the kernel. So, and when you make a mistake while modifying the kernel or adding features to it, if you make a mistake and your program crashes, well, your program is the kernel, so your whole operating system crashes and you have to reboot the machine. So it is definitely more time consuming, but I don't think it is necessarily difficult. I don't consider myself to be a Linux kernel guru or even a really good programmer. So if I can get away with doing this, a lot of people can. I have met a lot of good programmers who shy away from LKMs or even kernel programming just because of the myth that it is so difficult. It is not, but it is, of course, more time consuming. It is fun, and that is why I appreciate it. As I will show you examples on how to alter the kernel to change its functionality on the fly, so you can even write files from the root user, how to actually write a backdoor that listens on a port and does annoying things. And I will also talk about a project which I wrote about in the Linux journal a few months ago, which is something similar to what Tripwire included in test, but it does a little more. The problem with Tripwire that I saw, in my opinion, was that it was too passive for me. Tripwire, for those of you who don't know, is a tool that is run routinely, and it has a database full of hashes of files that you care about. And if it finds that the hashes of those files don't match, it will notify you. Well, to me that was great, but it's not required. It's not going to stop somebody from rootkitting your Linux files. What I did is took the concept of a tripwire, and built a Linux clone module that intercepted every time the function call responsible for executing programs and checked the hashes on the fly. So therefore, if you have a hash file that you care about and somebody replaces that file, well, it will not even let it execute, so it will stop the damage from being done. So this, in my opinion, is fun stuff, and gives you more incentive to research that game. Again, moderate C programming skills required. I am not a skillful C programmer. I consider myself a moderate C programmer, and it's not that difficult, as you will see. Before we get into writing a game, a bit more introduction to the Linux kernel itself. Although modules allow you to add functionality on the fly, so it can be considered that the Linux kernel is in a way supports modularization, but it should not be confused with the concept of a microkernel. Microkernel, on the other hand, if you heard about systems like Linux, microkernel is based on the principle that the kernel itself, the operating system, should be as small and tiny as possible. And the services associated with the operating system should run on a separate thread, and they pass messages back and forth. The concept of a microkernel is really great when it comes to academia, but if for a guy like Linus Torvalds to sit down and write his own operating system, if he would have embarked on writing Linux to be a microkernel, Linux would not exist today, because it is just so complicated and there's so much coordination that is needed to write a microkernel-based kernel that I can see why Linux did a monolithic kernel, which is what Linux is. There's a link over there that contains, if you go there, that actually contains whole news group postings between Linus Torvalds and Andy Tannenbaum. I always screw up his name. Andy is the guy responsible for Linux, and there's actually a flame war between Linux and him on why my monolithic kernels are better than microkernels. So if you want some fun and name passing, look at that. Quite cool. I see myself, I guess, as a game can achieve kernel functionality on the fly, which is really important, and I think it's the coolest thing. Because for people like us in security who want to understand how people write backdoors, for example, LTMs are the best thing on earth, right? If you were to write a virus on the Linux operating system, or you were to want to install a painful backdoor, LTMs are the way to go. There's nothing more powerful because you're actually modifying the operating system itself. But in some cases, code must be statically linked. What that means is, in some cases, it does not make sense, or it's impossible to write a Linux module. For example, the process scheduler, which is an integral part of an operating system, is responsible for figuring out which process is allowed CPU time, and based on a few algorithms. That is because Linux, like other multitasking operating systems, give you the illusion that processes are running at the same time, or they're not. The process only gets finite amount of time defined by the process scheduler. So things like this cannot be taken away from the kernel, and you can't write an LTM for it. It doesn't make sense. So in some cases, you can't write an LTM for kernel functionality. But if you can, in most cases, my personal opinion that if you are writing, if you're modifying the operating system, the kernel, the Linux kernel, and you patch the kernel, and not writing in the Linux kernel module when you can, then you're doing a bad thing because you're blowing up the kernel. so I'm always behind going the other team route and patching the kernel. So it's probably more of a personal opinion of mine, but I'm not satisfied with it. Advantages of LKM in general, no need to recompile the kernel. The first time I researched the Linux kernel and I changed a few things, I did not look at Linux kernel modules, I just basically changed the Linux kernel. And to implement a stupid project that is not even worth mentioning in these code, I had to reboot my machine 200 times in 3 days. Because every time I change the kernel, I have to reboot it, right? For it to take effect. And it was such a pain. So then, a few days later, I re-implemented the same thing as a Linux kernel module, and it took me 45 minutes. Just because I could unload it, load, and redo my changes. But I mean, there are times. That does not mean that you can't screw things up while writing a bad update. I'll show you how easy it is to also have problems with going the LKM route, but in most cases you're better off than patching the kernel. Now, it's easy to debug and develop. I need that compared to patching the kernel itself. I don't need that compared to application development. Another advantage of going the LKM route is, suppose you have a PCM-CI driver, right? And your PCM-CI driver is implemented as an LKM. So when you recompile your kernel, you have an option of actually making the driver for your PCM-CI part, for example, a module or a part of the kernel itself. If you go the module way, then you can, there are tools available which you see in the next slide that should be transparent to most of you if you run distribution, that load and unload the module on the fly. So that brings me to my last point where, for example, if you're not using PCM-CI card, and there's no reason for the code for that to stay in memory, right? Because if you patch it into the kernel and not a module, then it's just taking up space. And to me, even though a kilobyte, I still don't like it. If efficiency is a good thing, so I think LKM better. So if you think about it, a few years ago, when last time you downloaded a Linux kernel, at least I did, the day before when I got the latest one, the G6 one was what, 30 megabytes? A few years ago, it was 4 or 5 megabytes. And I understand that a lot of, you can't just, Linux being a monolithic kernel, you can't, there's only so much you can do. The only other option you have if you don't want the kernel to grow that big is to stop development, which is not possible. So Linux being a monolithic kernel, we can help Linux out by trying to implement LKM whenever possible. When I show examples of how to write LKM, we will be using a tool called insmod, which should be in every Linux distribution that you run. It's part of the module package. Insmod is basically a very dumb program, which given an LKM, which an LKM is basically an object file, and insmod calls the appropriate system call to register and load the module. Similarly, our module is a root module, and you can unload your module if you don't like it anymore or don't need it anymore. But if the module is being used for some reason, every time a module is being used, the module itself can increment the value called a reference counter. If that is not 0, or if another module is dependent on the module we're trying to unload, if our mod will not be able to unload it for you. The currently loaded module can be listed using a program called lsmod. Lsmod basically either runs the query module or also represent information in the processor to show to let you know which modules are running. really not applicable to a lot to my talk, but I thought I'd throw it there for people who are interested. The 2.4 versions of the Linux kernel support something called a KMod, which is basically a kernel thread that executes a user space level program called ModePro. ModePro is basically a program that looks at a file called modules.def, which contains all the modules that are needed for proper functioning of your distribution. And one module can be dependent on another one, and all that information is stored in modules.def. So ModePro works with modules.def to unload and load modules on the file. Modules.def is usually created by a program called depmod, which you should run or probably is practical if you want to return install or but that's all about loading on demand. Before we actually get into doing cool things, which I will talk about to alter the way system calls are called, let's first understand what system calls are. Most user space level programs run under a mode called user mode. The user mode is basically when the program is doing anything except calling system calls. They switch to kernel mode, also referred to as system mode, when an operating system is required. So, if you write a program, a C program, to open EBC shadow, which contains the hashes of the password on your Linux distribution in most cases. If you're not root, then you should not be allowed to read that file. So, for your program to request that a file that it needs to open a file, it has to go through the operating system kernel. There's no way that your program should be able to directly access the hard disk. That's not the way things work. The operating system is there to serve user-level programs, and therefore there needs to be a set of defined API for user space level programs, which are non-heritage programs, not part of the kernel, to request services from the kernel. So system calls is basically just that. System calls are a set of interfaces or gates for user-level programs to request services from the operating system. Every time we invoke a system call, something called a software interrupt occurs behind it. For our purposes, all the software interrupt is that it is related to our interrupt handler, which is defining the kernel, which gets woken up every time a software interrupt occurs. And if it's of type A, which there's a system call is being requested, appropriate actions are taken to serve the request. Now, the kernel itself maintains a data structure which is most useful for things we want to do. It maintains a data structure known as a system call table, which basically contains pointers, names or positions and pointers to the system calls exported by the kernel. Now, since, as I said, a Linux kernel module runs, when you write a Linux kernel module and you load it, it basically is the kernel, and it can access anything that is available through the kernel. So, when we write our system call, our LKM later, we will actually see how we can grab a hold of the system call table data structure, change it. So, for example, the open system call is called every time a file is open, right? So, we will see how we can alter that data structure to, instead of calling the real open, we will maybe call our fake and evil open function call. And when we are done doing the evil things that us hackers like to do, we will call the real system open. So the program that is running will have no idea that that is happening. If you're interested, look at skull.h and also entry.s. Entry.s is an assembler, but not an assembly program, but it's still an interesting file to look at. I'll show those to you next one. This is what this skull.h looks like. You'll see where we use the NI directives later. These are some of the system calls. There are a lot more, probably all of them you will find. There's about entry.s. Also, there's a definition of the system call table there, and it contains a list of all the system calls. Okay, now before I go on, I just want to make sure that you don't confuse system calls with library functions. A C library function, as a lot of you probably know, exists to facilitate portability. And that's one disadvantage, right? Because if you write a program that uses fopen, which is a general C library function call, if you write a program that uses fopen in Linux, and you take the same source code and you compile it under Sigma in Windows, it will still work. But if your source code is centric to system calls, then it's very probable that your source code is likely not to support. So, and library functions make things easier for you. They hide abstract away cryptic parameters that system calls usually require. Of course, there's a lot of debate on it. Some people say fopen and people don't use it, whatever. But their library functions are there to make life easier and facilitate your source code more portable. And basically, they wrap around system calls. So if you use fopen actually really calls this open, which is a system call, to do the work behind the scenes. The tt3 program is a really neat program if you want to research more what system calls are being invoked by your executable. tt3 basically makes use of a system call called ptrace. Ptrace is a system call that allows one process to monitor the other. Using tt3, there's a lot of cool things you can do. If someone hands you over an unknown executable, I don't know why you would execute an unknown executable, but if you were given that, then with tt3, hopefully you'll be very much or something to see what's happening. Or if, for example, when I was new to this system call thing, and I was more of a C programmer, a newbie, I used tt3 to gain the knowledge that type of blocks as well. So it's a pretty cool program, I think. So let's see. If, for example, take a look at this simple C program, which basically calls fopen to open passwords. And it exits a bit of course, and it displays the easy password. That's basically all this does. And assuming that program is called it out loud, if you want a trace like that with the -o option to output this output to a trace underscore output, and if you do it for a password, you will see that the open system call is actually called behind the scenes. So it's a bit pretty cool. Okay, so to intercept system calls, we have to follow some procedures. First is we put the system call table to call our evil system call instead of the real system call, right? And then it's very important in most cases to call the real system call when you're done doing evil things like that. Let me give you an example. When I first played around with intercepting your system call, I did a very, I staggered it and I loaded, I brought down the end and I thought did a lot of cool things with intercepting your call. For example, if a file name or if even root is trying to open a file called m slash whatever, it would not allow you to open it when the kernel was loaded. But in my intercepted system call, because I forgot to call the real system call, what basically happened was as soon as I inserted my Linux kernel module, finding that the system call table was altered, my evil open call was called instead. And after I inserted it, I couldn't do anything else. Because once, even if I did ls would would use the open system call to look at the directory structure. Everything failed. I basically had to power off the machine. So it's always a good idea to call the real system call when you're done. When you start system call most cases. In our first example, we will look at how to intercept the exit system call. Basically, exit is a system call that is called by user-level programs when they're usually a value of 0 passed to it signifies everything went okay, and a non-zero value in most cases signifies that something went wrong. So what we will do is we will intercept this exit function call, and we will print to the console the value parameter passed to it. It's just nothing out of the ordinary, but to understand how games work, we will just do this experiment so we can go on to much fun things later. When I present these next slides on how to actually do this, I'm assume this to be an example of a hello world application. This is very elementary, so I'm not going to go into so much detail when I talk about intercepting other calls. So this is just a skeleton for you. These slides are available on the Hacking website, and also my personal web page. There's a URL for that somewhere in the future slides. So all the code that I've presented is available. You should be able to download it and compile it, and all this should work, hopefully. Okay, so again, store the location of the real system call. That is very important, because if you don't store the location of the real system call, then you can't call it when you're done doing things you need to do when you intercept that system. And also, when your module is removed, it's also a good idea to replace your system call back, because once your module is removed, the memory allocated to that module is destroyed. So if you forget to remove your pointer to your hacked exit call, then the operating system is likely to crash, because exit is also called directly by the kernel. If you're, for example, if you write a user-level program, a C program that does not call exit is called behind the scenes for you, because exit is responsible for deallocating your program from the scheduler and its memory and all that good stuff. These are the headers that you usually need when writing the OPM. The sys is called H distributed because we are going to alter the system call table. The kernel in our case, we need to include it because it also contains definitions for print case, which is print at the kernel mode. And module.h, of course, contains a lot of directives and header information that you need to write a module. The external voids is called table is basically a directive for to tell the compiler or for the kernel to fill in. This is called table data structure as soon as the module is built. Think of it as just a way of accessing these. It's called table data structure. That definition there to do that. You guys just want to shut up about that, so you should, if you have done some other things in 2.2 or the 2.4 kernel, you'll notice that every time, if you don't have that module license GPL directive there, when you insmart or insert your Linux kernel, insmart will complain that the kernel is tainted. What that basically means is the Linux kernel is distributed under the new public license. This is politics, by the way. So it is distributed under the GPL, and according to Linus Torvalds and other folks, go back to GPL all the time. I do too, but not so much. According to their opinions, if you're writing an LKN, then you are basically altering the kernel. They don't see a difference between an LKN and for you to take this kernel source code and alter the source code. So basically, under the GPL, if you alter the kernel or any software that is distributed under the GPL and you redistribute it, it also has to be under the GPL. So, and this is also there to discourage vendors like NVIDIA who distribute binary only drivers. It is my opinion that this is a bad thing, though I kind of see where several people like this are coming from. I can see why it is a good idea to encourage everything in the world supporting the GPL license. But I think it's going to scare away a lot of corporations who are trying to put out drivers. But anyway, that's that line is there. Without that, responsible for playing around. Next, as I said, we need to store a pointer to sysexit. And before we do that, we need to declare prototype, which basically helps us store the pointer correctly. The prototype basically needs a name for it and the parameter of the success. If you don't know what the parameters being accepted by the system call you're trying to accept, well, that's a bad thing. Because before you accept the system call, it's better than what parameters are being passed to it. Either look at the command page or you go to the components and you'll probably see the definition of the number. In our case, it takes one parameter in, so that's how we would do the prototype. This is what our fake exit call looks like. So what we do is something very simple. We just print a this exit call is error code equals error code. So every time the system call is executed by any program after a code was loaded, a module was loaded, that message will show up. And like I said, when we're done, we will call the original system call. Because we want exit to do the work if that's right. Init module is a function that is called when your LKM is loaded. So here is what we will do initialization. And in our case, what we really need to do is store the location of the real exit call. And we do that by using our prototype that we defined earlier, or this exit equals this call table, which is available to us now, and our exit is basically a directive that points to the definition to the spot where the system exit pointer is. Once we have that, this is where we do the real work. That is, we actually manipulate the system call table and point the placeholder pointer to the exit call to our fake function. When it reaches this end and it's done, return 0 basically signifies that initialization went away. When the return 0 is executed, everything is fine. What basically happens is now we have altered the system call table to call our fake exit function instead of the real exit, and we call the real one when we're done. There is no. Okay. This is how you compile if you need the kernel and module directives there. You can do it back there and just put a hash define underscore and hash define module if you don't like to do it this way. And just insert it. And if you do an ls in a file that does not exist, ls will return a non-zero value, probably 1. And you should be able to see that. I don't have a, I didn't think I would go down for it, but let's try. So I'm going to use one. Okay, if I do an ls, right, ls exit with 0, and do an ls for non-resistive file. And as it exits with 1. Okay, and the word stuff. Oh, by the way, if you try my code on the Red Hat 9 kernel, even though Red Hat 9 I think till now still ships with 2.4 kernel, if for some reason they decided to not export the call table, as I was talking about later, bad news for us from 2.5 onwards don't export the system call table. But for some reason Red Hat decided to backport 2.5 and not export the call table. So if you want to Red Hat kernel to export the system called data storage. That is what this is what you need to do, or I actually recommend you install it yourself. Okay. Okay, in this example, we will intersect sysopen. As you can imagine, sysopen is the system call that is used to access a file. So in our case, what we would is we will take a file, for example, temp/test or temp/protected. Okay? And what we aim to accomplish with this module is basically, once this module is loaded, it will intersect all calls to open. And if the file that is being opened is temp/protected, it will not allow it. So it doesn't matter who you are. Even if you are root, you will not be able to access temp/protected. These are tricks that are used by a lot of backdoor authors to do everything. So if you're wondering why they really need to do such things. But just when we discuss this open, of course, a lot of us might first think that all we have to do is compare the string /temp/protected to the file we open. Well, not so. Because what if somebody creates a symbolic link to temp protected and then the parameter that is passed to open is the name of the symbolic link? The only sure-shot way of figuring out if the file that is being opened is the file that we want to protect is by comparing those files I know. If you know anything about file systems, basically every file has a data structure associated with it called the inode. The inode data structure contains a lot of things. When was it last accessed? What are the permissions? And all of that stuff. And it also contains another name parameter called inode. So if inode is basically sometimes used interchangeably to refer to the inode block number, which is unique to every file, or the inode data structure. So in our case, we're interested in the number that is unique to every file, the inode. And what we will do is we'll compare the inode of protected to the inode of the file that needs to be opened. And if they match, then we will return minus the access, which is basically an error code that we find that you can't open the file. So this is what a page open function looks like. Don't worry about name data, or actually worry about it. Name data is some data structure defined in the column. Name data contains another structure called dentry, which we are after. Dentry contains the inode that we really want. So what we'll do is we'll call user path block, which is a function defined in the list. What it basically does, it takes a file as a parameter, and it fills in the name data structure with all the appropriate information. So we do that first to the file that is being opened. And if everything goes okay, then we will have its inode, which is stored in the inode variable. Now, we need to do the same thing for temp protected to get its inode. But before we do that, there's a pitfall, right? The kernel memory is segregated or separate from user space memory. Therefore, when you execute user path block, like we did before, it expects the file name parameter to be memory for it to be located in user space. So if you actually look at the kernel code and look at the definition of user path block, there's actually a directive or a check made to make sure that file name is defined within a virtual memory space. I think it's between 0 and 3 gigabytes. It's virtual, not physical, virtual. And if it does not exist within that range, there's something wrong. So to get around that, what we will do is called getFS to get. I don't know what FS stands for. Last time I checked, it was really closely misnamed for some reason. what it basically does is it stores information in FS which corresponds to the current memory mapping, which segregates where user space memory is supposed to be. So we store that information, get the times the maximum amount possible, which is like 4 gigabytes, and then it sets the limit from 0 to 4 for temporarily, if you're doing this temporarily, just to make user path walk happy. Because when user path walk, make sure that between 0 and DS, it will now be 0 to 4, and so it will execute properly because it will be happy. Then we reset the memory map information back to the old when we're done. So basically what we've done now is gone around the distinction between user space memory and user space memory to execute user path walk properly. So hopefully when we're done with this, what we will have is INOs for okay, so you're wondering even more, temp class protected because we have defined it in the kernel. It actually is allocated in the kernel space. That is where the problem comes in. You see this, there's quite a distinction between something allocated in the VM, which is in the kernel space, than finally which is passed to us from the user space as a program. If everything works fine for now, there's no error. User path log does not return an error. We basically get the INO of our temporary file. And we now match the INO of the file that needs to be opened with the INO of the file that we're trying to keep that. And if they match, then this is the file that should not be able to be opened. And we don't mind the access. And when we're done, they don't match or if something went wrong with the user path log, we go ahead and let open execute the way it was supposed to. So I think in my okay, instead of temp protected, I call it temp high. Temp high, as you can see, does not exist. Assuming I've booted somebody's box and I have my module here, which I've sure called open.o, and then I try to look at temp. Now notice I'm root, right? Even though I'm root, I can't access temp because the kernel module has intercepted and said open and is preventing it. Now let's move it. So basically, it gives you an idea of the tricks that people use to fool even the root users. What are the things that are fundamental to writing a backdoor application? Now you look at writing a backdoor which basically listens on a port. It's an MKM, which basically listens on a port, and every time it's connected from a remote machine, it will alter the system call table to call out evil open call instead. And every time you connect to it, every alternate time you connect to it, it will replace the original system call, open system call. It's a great way to not accomplish anything great, but great places in my people. The thing is, I don't want to stand here and actually walk you through a full-fledged backdoor that serves the shell. I just want to hopefully use presentation to give you information to make you understand how people do things and do whatever you want to do every time. So, in our original module, we'll basically do the same thing. It will store the location of the origin of the server. Then it will call the appropriate kernel call to create the socket, find it, and listen to it on a particular port. And then it will invoke a kernel thread to basically serve incoming connections to that port. Same concept that you would use if you were at a user space level server. But we are not, in this example, in this elementary example, we are not going to go as far as to spawn a new thread for every incoming connection. We're just basically spawning a kernel thread to serve one kernel thread to serve incoming connection. So when you run this module, if you connect more than once, then you will be queued. This module does not handle concurrent connections. The do server thread which is spawned by a module basically does have a very simple. It's a while module which executes forever. Call the accept call to block on an incoming connection. And flag is going to set to 1. So first time, what it does is it resets this open, and every next time it's called, it frequently open. Writing code in the kernel, or in LKN for that matter, to do socket programming is not a recommended thing to do. But the makers of KHTTP think otherwise, and I really love it. The KHTTP is basically a kernel-based web server. I really don't. Apparently, it's really fast, but I mean, it's one of those projects that you look at and you say, they just did it because it can be done. Yeah. So, if you look at that paper and also the KHTTP sort of, there's a lot of missing things. They've painstakingly done so many things to do socket programming in the kernel space. It's really amazing. I got much time to do this from it. Let's look at how it runs. So let's go back to step 9. You can access it now. Let's use more insert card module. Right. So now our module is loaded. We can still access /hop, right? Now assume the person who installed this backdoor connects to us remotely. Now I'm doing it for my own local host, but assuming it's remote. So someone connects to our own port 9998 and disconnects, right? Now we can access it. So someone installed a backdoor remotely, and even though I will show you how to hide our presence in LS1 and all of that, this is what backdoor authors do. In most cases, I don't even think you need to go that far. I mean, for a regular Unix or Linux administrator, if something like this happens, I would think it's a problem with the kernel or something, right? I mean, when was the last? If something like that would have happened to you, if you're not a Linux module guy or have not studied backdoors, you'll be stumped, right? And this is a really cool thing. But people have gone even further to hide their presence from LS1. So again, if I reconnect to that port and disconnect, now I can access that call again. So imagine if somebody did that to easily shadow, no one can log in, right? Okay, proc KSYMS is basically a magic file. Right? The proc directory, if you look at it, contains magic file in most cases. It contains information that the clone wants to give you at a particular time. If you look at prop ASYNS in particular, you will find the kernel symbol table. What that basically means is, let's look at it. If I do a scan from ASYNS, one of the things that we really need is the syscall table, right? Sure enough, syscall table is in the kernel system called kernel module. Kernel symbol table. There are a lot of other things. Let's do more on it. Let's see. Let's actually insert our exit call. And if you do a more on prop ASYNS again, you'll see there our quick exit function appears. Right? So that is one. Prop ASYNS is actually a good place to look for stuff that is exported by Soma at any given time. But there are ways to get around that. If you use the export no symbols macro when you write to LKM, it basically tells the compiler or the kernel that you don't want to export any symbols from your module. So then less things will show up. For example, the name of our intercepted exit call would not show up, but still enough information will show up to signify that our module is loaded. To do more, what we can actually also do is intercept this open, and every time prop ASYNS is being opened, use the example I gave you earlier and manipulate access to that so you can actually hide the presence of your module from whoever you want to hide it from. Prop modules contain list of all currently running modules. Again, you can intercept this open and do bad things, such as if prop modules is being opened by anybody, don't allow it, or even by displaying the prop module, we can just hide the name of our module. Place paper on Frank 52 Article 18. He or she probably talks about how to, in real time, alter the kernel module structure. Now, the kernel itself has a structure somewhere, which contains a list of modules running, their respect counters and all that information in there. So if you could actually directly manipulate that, you can do much more and have it almost disappear from module. So that paper actually talks about that and gives you specific source code to do that. tt3 tutorial called Completion Delivery Kernel Modules by Pragmatic is the Bible for using LKM to do a lot of cool things. They talk about how to write processes. Again, as I said, prop is a directory containing magic information. What I basically mean by magic information is even though when you look at the prop ASYNS, it appears as a file to you, but it's not a file of context. And the prop directory was historically created to share process information. That's why it's called prop. So if you look at the prop directory, you will see directories signifying the process ID that the process is running and lots of information in there. So this tutorial actually talks about how to hide processes. So if you can actually write an LKM, so if you write a user space level web server that's listening on port 9000 or even a backdoor shell that serves the shell, and you want to hide that process, you can write an LKM to basically do that developing in the paper. They also talk about how to hide or how to basically parse or play around with dev schema. Dev schema is basically the kernel memory. If you can play around dev schema to do cool things, then that's actually the progress we should do. It's probably one of the most difficult things to do. And tools that check for dimensional module backdoors basically directly look at dev schema to check if something bad is going on. So if you can, that is really advanced that we talk about. Hiding modules, what we talked about basically, that also mentioned user endpoint space memory management, like what we saw in our previous this open example. They talk about how to wire much more detail than I did. Basically, the problem is, as you can imagine, memory that is used by the kernel is segregated from the process memory, and each process also has its own segment of memory that, in most cases, it will not share with other process. And the process should not be able to directly alter the kernel memory because it will let you do any kind of security. That's impossible. So because of this segmentation between kernel memory space and user space, we have to take a lot of care when doing interactions with user-level programs. So that detail is in PhD paper and also some other techniques. Mod exec hash demonstrates how bad I am coming up with project names, but it's one of the projects I worked on when I was in college. Again, when I looked at Tripwire, I appreciated what Tripwire did for me, but I didn't feel safe with it for some reason. Well, the reason being that it only Tripwire basically tells you how you've been had after you've been had, and that is not much use to me in my opinion, unless we could do something real more proactive and not execute or Trojanize binaries, for example. So I teamed up with one of my professors and we did an independent study course where we developed an FPM which intercepts sys-exit VE, which is a system called every time binary is executed. And what we do is at one time calculate the hash of the binary that needs to be executed and calculate the known hash of that binary. If they don't match, then we don't even allow it to execute and we lock it. So basically we're doing kind of what Tripwire does, but we're being more proactive and not letting the damage happen in the first place. I've only spent a few days coding this, so this is there to show as proof of concept code, and it is there available for you to go to better things with this. Don't install this on mission critical machine and think you're safe, because there are a lot of things I have not done thoughts around to do. For example, protecting the hash database itself. Talk about things can happen. Just proof of concept. It's one hobby. The source code is out there, and I'm definitely happy with it, even though it's not yet fully done. So basically, this is what I do. Intercept secondly, and compare the animal of the file being executed. Compare it that to the one in the database. If the animals match, then we know that this is a file that we care about, because an animal of that is present in the database. A database, when I say database, it's just a plain text file. It contains the inode of the file and its hash. And if the animals match, then we will go ahead and compare, then compute the hash of the binary being executed in real time, and then compare that hash with the hash in our database text file. If they match, everything's fine. We call the real activity. If they don't, then we terminate activity and we don't allow for them to be executed. That is basically it. There are other features I also said. this unlink, which is there to remove files so no one can remove or alter, or even access this open so no one can alter the module itself. For example, someone can replace the .o file, and every time you reboot and you reinsert it, something bad can happen. But if you look at dev, if you look at the way hard disks or devices are handled, right? If you look at if you have an IDE drive, sometimes their flash needs to be 1, 2, 3, depending on partition. Now, someone who has root and has enough time can actually alter device file directly. So that is something that I don't have protection for. I don't know yet of how they would have a protection for someone accessing a device directly. But it is so difficult that if you want to do that, good luck. It is available on that website. Usually the repeat if you're going to use it, because if you don't do it right, you can call it your machine. MakeHackTV is basically a shortcut which takes all the set UID files in your system and outputs hashes for it. So first thing we need to do is one hash shortcut to create a database which contains a list of all the files we care about. In this case, I'm just assuming we care about the set UID files. Probably not to specify here. If someone really wants to use this, so they will add more files that they really care about. And then just insert insert a module. The way to test it, which I will show you in this demo, is basically use a written password to get the set UID program. It sets UID because, as you know, a set UID program always executes under the privileges of the root user. So for you to change the password, you actually have to, for example, alter the shadow file which only root can write here. So password is the utility that PSSW utility in Unix or Linux that you use to change your password. And you don't have to be root to do that. And because it says UID, a flaw in password can get you to a different password variable. But anyway, so when this module is running, consider if someone breaks into your machine and installs a rootkit. A rootkit is basically, in most cases, a collection of Trojanized appliances. For example, if he or she breaks into a machine and installs a Trojanized version of PSWD, which when you run it, basically does a lot of other things, such as mail that person your shadow password file behind the scenes, and also execute the password functionality, so you as a user don't see it, right? So for our testing purposes, what we will do is we'll take a binary called ls and copy it over the password. So basically, and then we'll go ahead and try to run password, and if all goes well, it should not be allowed to run because the hashes won't match up. See that one that I didn't have a GPR version, ignore that. So I already have a copy of password that you can see here. So what I will do is copy bin ls over user bin password. Right? So in normal scenario, if I type in password now, you will actually see a file listing because we replace password with ls. But in this case, password will not be allowed to execute because our module realized the fact that first, password, the unknown for password, the password is actually a file that we care about. And the hash that we have already does not compute with the hash, which is in this case the hash of ls. And so the damage, unlike tripwire, they're preventing the damage from being done in the first place. And I also have some functionality so you can remove tt3 dash. So I intercepted the I intercepted the delete module system call so as to prevent somebody from unloading a module, because if someone came through, first thing they want to do is remove one module. And I also intercepted create module because I didn't want any more modules being loaded after reloaded, because basically what someone can do is assuming we have intercepted this exit read, somebody can write their own module and re-intercept this exit read and allow everything to execute the way it was before. Therefore, bypassing our module condition. Calls 2.5 and above. System call table, all the system call table on the slide. Hook system call is a great thing for people like us who like to do legal things. But it is generally, I kind of agree with Linus and whoever was responsible for making the decision that 2.5 onward system call table, data structure is no longer exported. What that basically means is you can't hook system calls anymore from 2.5 onward, which is okay for us for the time being, because by the time 2.6 catches on production machines, it's already a while. The reason for that is it's not clean, which I can understand, because if you, for example, write module A, which intercepts this open, and then module B also intercepts this open, then really module C will be intercepting the hacked open of module A, and if module A is removed before B, then B will actually pointing to or calling a system call that no longer exists because you removed A. So it's not a clean way of doing things. And basically from what the dialogue that I've seen passed around in news groups and all that by Linus and other folks, it appears that there seems to be no incentive for exporting to the company aside from facilitating backdoor writers to the backend. So for now, 2.5 and 2.6 will not export a system call table. There are also licensing issues. It's this whole thing that it comes back to the GPL director. For some reason, they don't have this way. But for those of you who want to study hooking calls in 2.5 on their examples, there's the Linux security module project that was started by someone in the NSA, I think, I'm not sure. And it is currently patched into the latest 2.5 releases, which basically contains a brand new interface for hooking system calls to a certain extent. I have not studied that, but there is probably the reaction really people if you want to research hooking. Or just have to start with 2.5 onwards. So for everything that I talked about is available in this URL, also available on the Hacking websites. Question and answers relating to everything that I have talked about. If you want to talk about anything under the sun about it, come to me after. Any questions? Come on, the last guy got two. No question. Okay. Here are resources that I used to do my research. All of these are great resources. Hopefully here in my slides. So once you understand the code and the stuff that I presented, you should have no problem picking up where these papers are. Special thanks to my professor without him I would not know what I do about games. And also, if you have very good reason to write this talk, be sure to check out the talk by Red Rackets, who was also from THC. And his talk is basically a lot more advanced, basically going to take off where I'm going to talk about advanced monomolecular, which is a really cool thing, I believe. So hopefully this material will help you do a good. Thank you.